Hi, AP Chemistry. We are going to take a look through the AP images. So what this document actually is, I went through a couple old AP tests, and every time I saw a picture or a chart, I just snipped it out of there and uploaded onto this document. So, one of the most important things as you are taking AP tests is that you're familiar with the type of questions being asked. So if you can look at an image and that image kind of, rings a bell in your head and says, oh, I need to be looking at rates, or I should care about intermolecular forces, it really does save you time and effort, and it allows you to, quickly look on your cheat sheet to kind of what you should be thinking about moving forward. So before you even start this video, you should have gone through it on your own and put down the work or the things that you think it is. So I would suggest doing that in one color, and then you should have revisited it, looking back at Google, looking back at previous notes, looking at your ebook. Probably use a different color as you mark it up like that. And then I am going to go through this with you. I'm going to go pretty quickly. So if at any point in time you're like, oh man, what did he say? Just pause the video. Videos are neat. So you can just pause it, look at the words I have written down. But I'm just going to quickly explain kind of my thought process with each of these images. All right. As you can see, the document, if you were able to print it out, remember that's in the top right corner. All the documents are going to be in the top right corner for these e-learning days. If you can print it, great. If not, you can just have a piece of paper. If you just have a piece of paper, please sketch out the image of what you are actually looking at. That's powerful information. All right, so we're going to go ahead and look at this. Let me rearrange my camera here. All right. So hopefully this looks good for you guys. So I'm just gonna flip through these different pages, and again, just kind of talk over what my thought processes were. So again, if you need to pause this, go ahead and pause it. So this one happened to be snipped out of a multiple choice question. It was really, what is the arrangement of these things? So this is right away, it's a molecular picture. You care about charges. Remember, opposites attract. So the answer for this one would actually be what? So you have a nitrate. Nitrates are completely soluble, so D would not be your correct answer. And then you're looking at the Mickey Mouse molecule, right? So we know it has opposite charges. You know that you would rule out C just based on the fact that the same thing is happening in both pictures. So then you're choosing between A and B, and opposites attract, which would lead us to choice A. So it was really, the question was, what would silver nitrate look like at an aqueous level? Moving on. These diagrams here, I got my YouTubes are still in the way from electrochemistry. So moving on here, we are looking at a bond length diagram, and you're looking at the relationship between bond strength, really, and bond length. So how much energy is in the bond? So those dips tell you where the bond actually happens. And so you get a relative, amount of energy, and you also have a relative distance. So maybe up here, it would say you have X, Y, and Z, which one would represent maybe a double bond versus a single bond. So, or which one would represent a larger atom or something like that. And so you should be able to mark that stuff out. again, when we're talking about the internuclear distance, we are looking at the space between our atoms, right? So this is actually how we can figure out or guesstimate atomic radii. Again, if I'm going too quick, remember you can always just pause this video, copy down what I have. These best fit lines, this is a Beer's law plot, y equals mx plus b. So we're looking at the concentration of an unknown solution. Remember that this only works with colored solutions. Some colored solutions that we have seen this year in class were copper, iron, cobalt, and nickel solutions. If you're talking about like zinc nitrate or sodium chloride solutions, you cannot do a Beer's law curve with that because those are just clear. We also did potassium. I ran out of room, but we did permanganates, right? It was that purple colored solution in our rate lab. Moving on, this is an intermolecular force diagram. So here we are looking at a representation of hydrogen bonding happening. Remember, hydrogen bonding is the strongest of our polar attractions, our polar intermolecular forces. Remember, it has to be unique though. It's H attracted to a faux nickel, and that H also must be connected to a faux nickel for hydrogen bonding to take place. Doesn't matter how big or what the molecule looks like. This was a representation of hydrogen bonding. Moving on, this was way back in August. We learned about these PEs diagrams. So the PEs diagrams represent, we have these different energy peaks. So it relates to how much energy does it take to remove an electron. And these are relative numbers. This intensity over here to the left, it's a relative number. So the more energy you have, the harder it is to remove that electron. There was another, that one kind of rolls forward. This is also a PEs diagram. And so just a different way of looking at that. Each peak represents something, right? So you can, based on the photoelectric spectrum, you should be able to figure out what element you have. So this is a 1s2, 2s2, 2p5, right? And so what element is that? You could look at a P table, figure it out. Pay attention to scales. As you can see, this binding energy is decreasing, where the other one's binding energy, it is also decreasing. So it's a weird looking graph. Pay attention to that. PEs diagrams are known for that. Titration curve should be pretty fresh on your mind. Do you remember how to find your equivalence point? And then looking at, hey, are we above 7 or below 7? What does that mean? Also, remember we have a half equivalence point. So the amount of solution that is added to get halfway to the equivalence point. So like if my, these are kind of bad. If my equivalence point was at 20 up here, my half equivalence point would then be at 10. So at that point, the pH equals the pKa, and we could figure out some information about a weak acid. All right, we have two heating curves on here. Can you look at a heating curve? Your mind should go to Q equals MCAT. Do we remember that our plateaus represent boiling and melting points? Changes in temperature are on the slopes. Could you discuss what the molecule changes look like? So on the back, we continue with heating curves. Again, on a heating curve, even though the temperature is not changing here, we are changing our molecule type, right? Maybe from in this case, a liquid to a gas. So a liquid to a gas, our kinetic energy is changing, right? Our potential energy is changing. So what does that look like? Can you represent that? Can you answer a question with that? Again, as we're looking at these things, the main point is getting your mind in the right set. So you come across a question, here's a graph. Is your brain going directly to rate laws? All right, so here's a natural law. Remember, it's natural to want to be first. It is kind of inverse or a backwards way of thinking to want to be second place. So can you do that right away? Next one, potential energy diagram. So you're looking at activation energy. Is this endo or exothermic? This one happens to be endothermic. You're absorbing energy. Can you pick out your activation energy, which is right here, 150? And this graph with the dotted line just so happens to be looking at the dashed line with a catalyst, the solid line without a catalyst. Moving on, we're looking at some molecular structures. So can we look at these molecular structures, and could we talk about what is happening, with the boiling point, melting point in states of matter? So with butane, it is nonpolar. Here we would have some H bonding. Here we would have, it's just polar because this is going to be trigonal planar here in the middle. All right, so would we be able to know that, propanol has the highest intermolecular force, therefore its melting point and boiling point would be higher. And this would be opposite. Lowest intermolecular force, low. All right, moving on. Here we are looking at just a table. Here's a table. If you look at it, we heat it, and eventually the mass isn't really changing. So this came off of an old FRQ talking about why do we have to heat it multiple times to get a lower percent error. This was last week, right? We just did electrochemistry. So does this look, this is how they draw galvanic cells. And so you should be able to figure out a bunch of things about them. What is reduced? What is your cathode? So then what is oxidized? What is your anode? Keeping these 3 points fresh. You would not be able to do that without seeing your half reactions. And with this info, could you determine this stuff? So again, what is actually happening within the reaction? So this is tin plus 2. This is copper plus 2. So we would not, we would not be doing that. We would not be doing that. Those reactions would not be taking place. These reactions would be taking place. Could you figure that out based on the formulas and go from there? Look back at last week's notes if you don't feel like you could do that. Here's mass spectrum data. Again, this is going back to August, September. So each of these peaks represents the mass of a different isotope in this case. Could you calculate the average atomic mass? Could you figure out there is 1, 2, 3, 4, 5? There are 5 isotopes in this particular representation. So every single bar is a different isotope. Sometimes you can figure out different elements based on this as well. It would look a little bit different, but same information, mass of an atom versus how many you have. Moving on, we're looking at types of solids here. So everything is relative, right? If you look at B is a compound. These things are attached to each other. That represents a bond versus A and C and D. They're not really smushed to each other. They're just kind of touching each other. So these represent just mixtures. This is ionic with the charges. Here we have big atoms and small atoms. Here our atoms are relatively the same size. That stuff all matters. Look at a P table to remember atomic size. Here's a multiple choice question, kind of just saying what one represents cold versus hot. Remember, vectors relate to speed. The longer the vector, the faster the thing is moving. So maybe you could say it's hot or cold, or these could be heavy molecules and these could be lighter molecules. Moving on, ionization energies. So when you look at a table that has ionization energy, See how there's a giant jump between the third and fourth ionization energy? That relates to valence electrons versus core electrons. So it's relatively easy to lose your valence electrons. It is very difficult to lose core electrons. So that all relates to each other. So that would say, this thing is in probably group 13. Has 3 valence electrons. Moving down, we have some weak acids here. So we just have multiple dissociations. Compare to see what happens most. So, like, obviously the first one happens the most. Also, in terms of pH calculations and stuff, your calculations would be based on that first step. These would change the pH by less than 5%. All right, a couple more pages here. Here we're looking at a molecular representation of gas phase reaction. So can you look at this and see, how does the pressure change? So you're really looking at a mole relationship. Moles equate to pressure. Could you do that? So we have less moles of gas after the reaction, so we would have less pressure. Here's a kinetics rates thing. So looking at concentration of time, you could find the slope based on this data, just looking at rise over run. Here's another Lewis structure, really just looking at strengths of acids. So which one of these two would the hydrogen be more likely to leave? It would be over here because we would have a larger electron cloud, a larger negative charge here. So H plus would be more readily available to leave here versus here. Again, strong versus weak acids. Here we're looking at reaction mechanisms. So remember, slow steps are your rate determining step. You can find your rate law based on that. Here is another reaction energy diagram. Again, you could find activation energy. Is it endo-exo? Each of these humps represent how many steps are happening. So like this thing here would have 2 steps. It would actually look like probably be you would have a slower first step and then the fast second step. So the slower steps have high activation energies, fast steps, lower activation energies. And then moving on, here's another way to look at rates. So you are looking at initial rates of formation. Remember, as one thing doubles, the other thing stays the same. The initial rate of formation is 4 times greater. So that's going to be a cubed relationship, second order versus first order. And you can come up with a rate law. Here's paper chromatography. We actually did this lab a long time ago. So remember, likes travel with likes. So if this was hexane, a nonpolar solution, X is traveling with hexane up the paper more. So X would be more nonpolar than Y, or X would be lighter than Y. Separation of mixtures using intermolecular forces. When we did this, we did an ionic compound, salt water, and alcohol, a polar compound. And look back at that. We did it with food dyes. Can you draw a Lewis structure? Can you quickly draw a Lewis structure? Come up with these, basic rules, right? We typically aren't breaking rules on AP tests unless it says, hey, how's the formal charge change this thing? So also, can you label trigonoplanar shape? That would be its molecular shape and its electron domain geometry. This molecular shape for oxygen would be bent, but it would be tetrahedral for electron domain geometry, and this would be tetrahedral and tetrahedral for molecular geometry and electron geometry. This would be a polar molecule. No hydrogen bonding happening here. This hydrogens are not connected to a faux nickel. Down here, looking at KSPs. KSPs compared to solubility product constant. So it would look like that. So could you solve for X given this information? Could you look at these and say which one is the most soluble or the least soluble thing? Here's a Maxwell-Boltzmann distribution. So we are looking at what gases travel faster and maybe why. So hydrogen would be the one traveling faster because it's lighter, right? This has a molar mass of 2 versus a molar mass of 4 for helium. All right, last one. Again, looking back at Lewis structures and intermolecular forces. So I just labeled these things. Remember, the higher the intermolecular forces, the higher the boiling point is going to be and melting point. And you could also draw some similarities. So remember, likes dissolve likes. So what would that look like in Lewis structures? Here we're looking at Le Chatelier's principle or just equilibrium problem. So our equilibrium is greater than 1. Remember, equilibrium is products over reactants. So you could say what side is favored, so on and so forth. And then we end with absorption spectrum. This relates to Beer's law. So remember, we are looking at peaks to figure out what wavelength we should pick to analyze things in Beer's law. Remember, our spectro-Vs or our spectrometers do have limitations. For us, the absorption, if it was greater than 1, it was kind of garbage. And if it was around 0.2, so you want to keep between 1 and 0.2 to get good, accurate data in doing that. So again, I hope you added stuff to this sheet as we go through things. The other thing you are doing is the first review packet. Again, take your time with it, answer that. My vision is to then upload the answers to week 1 stuff for next week. So, what that means for you guys is you should do the work, and then next week for week 1's review packet, submit it to me, and then next week I'm going to share with you the answers. You're going to go back through it and make corrections if corrections need to be made. Same thing with FRQs that we do in the future. So when you review things, it should, brain research says you do what you know, you go back through, you consult a book, you consult your notes, and then you go back through with the correct answers. And each time you revisit that document, you should be marking things up in different colors so that your brain knows, oh, I didn't know that, and it makes those extra connections. All right, I hope that was beneficial for you. Have a great weekend, everyone. See you next week.